Welcome to the third video of the series. In this video, we're going to talk about struct, enum, and pattern matching. Well, ownership keeps your data safe. But now the harder question, how do you shape your data in the first place? So far, we have learned integers, boolean, string, tuples, they carry the values, but none of them can create a game character or player and define this status. We can do that manually by defining each of these players, but let's say there are thousands of players, and that would be manual, tedious task to do. Well, two of the tools fixes that. A struct gives your data a shape with a named field that you can choose, and enum gives it a set of choices, one of which holds at any time. And pattern matching is how you read them back safely at a compile time. Let's dive more into that. So let's go. This is a struct. The struct keyword names a new type, a type you define yourself. We are calling this one player because we are modeling a game character. Inside the braces, there are fields. A name of type string, a score, an unsigned 32-bit integer, and is alive is like a boolean. Each field has a name and a type. Together, they may describe what every player must hold. If you notice, we used string, not the ampersand str or string from earlier episodes. This is deliberate because when the struct owns its data, the data lives as long as the player does. References inside a struct works too, but they need lifetimes. That is a later chapter topic, but I know we introduced the concept. But for now, the struct owns what it holds. What we have written so far is the shape, the blueprint. It does not create a player yet. Writing the struct gives you a type, nothing more, nothing less. But if you want to get a value, fill the shape in, each field gets a value. Then we will have one player, mouse score 0 is alive, and one value of that shape is completely ready to use. You could try to model a player with a tuple. You can use a string, a number, or a boolean. The data fits, but look at the line. What does each piece even mean? I bet you cannot even tell. Well, a struct names each piece. Over here, name is a string. Score is an unsigned 32-bit integer. Is alive is a boolean. Same three values, same memory. But now anyone reading the code can tell each piece represents, like they have this understanding. And the compiler reads these names, misspells a field, and you get this like compile error before the bug even runs. Names are not just for you, they are like these guardrails. 2 or 3 obviously related values. A tuple is fine. Beyond that, give the pieces names. You should really use a struct. To name a player, we need to name the struct, open the braces, and fill in every field. This is Meow, score is 0, still alive. The compiler will never let you skip a field. Now let's go ahead and read a field with a dot, meow.score. If you want to change it, then the whole let has to become mutable. Then let's mark it with mute keyword, and then the meow.score equals to 100 works. In Rust, the whole instance is mutable or none of it. You cannot mark one field mutable on its own. When a local variable already has the field's name. Write it once. Name maps to name. Score maps to score. Same value. Less noise. This is field shorthand. Now let's see, if you need a copy with one thing changed and just sets like one of the small thing different, then two dots brings back the old value and the rest of the field comes from there. Here Meo comes back to life. Now there's one important catch with this. The two dot actually move the non-copy field out of the old value. The player's name is a string and string moves. So after this, you cannot use meo.name anymore. It is gone. If every field were to copy no move, then otherwise you can just plan for it. Now the thing is, if you fill once and shorthand, when the names match, two dot to take the rest from another value. And remember, the rest may move, who knows? Sometimes you want a tuple but with a type name. Rust has tuple structs for them. Let's look at this. Struct position, then two I32s in parentheses. Now position is a real type. You reach the value by position 0.0 and 0.1. Now the catch that surprises people is define two tuple struct with the same shape. Inches wraps U32, centimeter wraps U32 also. To the compiler, they are different types. Pass an inches where a centimeter is expected, the compiler would stop you. The shape is identical, but the identity is not. On the other hand, the unit struct spawn, a semicolon done, no field at all, just a name useful as a marker type. We will see why in later episodes, of course. But tuple struct is for positional, unit struct when the name is the data, name field most of the time. Let's take a real problem, the area of a rectangle. The first version takes two numbers, the width and the height, and multiply them and it just returns the value. Well, it works, but let's take a look at the signature. The width and the height are floating side by side. Nothing in the code says they belong together. Well, if you try grouping them, a tuple holds both. Now area takes one thing better, of course, but which element is the width? Which is height? The dim.0 or dim.1? It kind of tells you nothing. The caller and the reader both have to remember. Now, if we use struct, and let's take a look at this. The struct rectangle has a width and the height, both named area. Takes one reference, the field access reads like a sentence. rect.width times rect.height. Same answer as before, but the code becomes more readable and it tells a future reader exactly what each piece is. It's like same answer, same intention, but clear and more readable option. The three steps, same number, each step made the intent harder to lose, and this is why we reach for a struct for these specific cases. Now we have a rectangle. We want to see what's in it. You can type println and give it to the rectangle and run. The compiler will stop you. The message says the rectangle does not implement display. Display is the formatter for end users. Rust does not write it for you automatically. So there is a second formatter built for developers, which is the curly braces and colon question mark. This is like a debug format. Try it and compiler will stop you because rectangle does not implement debug either. Same problem, different formatter. Rust still wants you to opt in. Well, let's opt in. Opt in with this line. Derive and debug above the struct tells Rust to generate a debug printer for you. Now, if you do this, it just works. The rectangle prints as Rust style record, and if you do this, it prints it. One field per line and easier to read in real output. One more tool is dbg. It's like a macro prints the file, one line, that expression and the value. It also hands the value back, so you can drop it in mid-expression without breaking the code. The derive debug to C and dbg, this trace, both comes before you reach the debugger. Data lives in the struct, but the behavior lives in an implementation block. Everything written in here belongs to a player. The struct holds what a player is, but the implementation block holds what a player can do. Most methods take $self and describe borrows the player, reads its field, and gives back a sentence. The $self is shorthand for the whole, like more verbose self : $self. It's like the same thing. You will only ever see the short form in real code. Now look at the call side. We write meow.describe, but not $meow.describe. Rust adds the reference for you. The compiler sees that describe once $self, so it borrows meow automatically, less noise on the page. Now compare new. No self, new does not act on the player. It builds one, hands it back. We call it on the type player : new, and there is like an associated function. It belongs to player but does not take a player. It's like the constructors live here. Same player type, function that builds it, method that reads it, method that changes it, method that consumes it, all in one place. And this is what the implementation block does for you. Every method asks one question. What does it need from the player? Read only? Read and change? Or take the whole value away? The answer picks the self. Only reading, take $self. You borrow the player, look at the fields, and return what you need. And the caller still owns the player. Most method lands here. Start here unless you have a reason not to. Now, changing a field in a place, well, then take $mute self. At points, raise the score, and the caller still owns the player afterwards. Same rule from like before episode 2 or something, only one mutable borrows at a time. But the compiler will not let two pieces of code change the same player together. Now, if you need the value itself, you just take plain self into name, solos the player, hands back the name string, and the original player is gone. When would you want to do that? 3 reasons. 1, you're converting between the type. 2, the value is huge and copying would be wasteful. 3, you want to build something step by step, like a builder chain, maybe. In doubts, you can always start with $self. Promote to $mute self when you need to write, and plain self when you really mean to consume. Methods can take more than just self. Here, can_bid borrows the player, plus another player to compare against. Self is always the first parameter. After that, method look just like any other function, name types, return types, all that. At the call side, you pass meow.canBit and the other player in the parentheses, and the compiler still does the automatic referencing on meow. But the second player you reference explicitly, the ampersand is on you because it is normal argument, like it is like a normal argument, not the self. One more thing, you can split methods across multiple implementation blocks for the same type. Both block belongs to the player. The compiler treats them as one, useful for grouping by purpose. Constructors here, queries here, mutation somewhere else, maybe. Methods take what they need. Self comes first. The rest are normal parameters. And the implementation block can live in more than one block. An enum is a type that is one of a fixed set of options. A player's status is one of them: playing, paused, or hit by, game over. 4 options, one type. Whatever shape the status takes, it is always one of these 4. Here is the part worth slowing down on. A player is exactly one of these at a time, never 2. If you try to track these with Boolean, you would write 4 flags: is playing, is paused, is hit, is game over, and nothing in the code would stop 2 of them from being true at once. The enum makes that impossible. And Rust enums are not only tags. Hit by carries a number, the point the player just lost. Game over carries a named field, who ended the game. The data writes inside the variant itself. One type, 4 shapes, and some hold data, some do not. All status. A unique variant is the name on its own. Status, : playing, no parentheses, no data, just a tag, like a C-style enum, similar to like C language or something. This is one of the simplest kind and the only one most other languages gives you. A tuple variant takes values in parentheses, like hit by of 2, and the number writes inside the value itself. The variant tags and the data are part of the same thing. A struct variant takes named field the same way a regular struct does. Game over here carries a hit like a by field, a string saying who ended the game. It is a tiny struct living inside one arm of the enum. Now look at all 3 together. 3 different shapes. Some hold no data, some hold one value, some hold named field. The compiler still treats them as one type, status. And this is the trick that makes enum so powerful. Same enum, like 3 ways a variant can hold the data, always one type underneath. In a lot of languages, any reference might secretly be null. You call a method on it expecting an object and you get like a crash. The bug hides until the runtime. Sometimes it hides until the production. Well, but Rust has no null values. If a value might be missing, the type itself says so. Option of the player, 2 variants, some holding the player or none holding nothing at all. Both are part of the same option type. You always know up front that by looking at the type whether something can be missing. And here is what compiler will not let you do. You cannot use an option of I32 as if it were an I32. Try to add want to it, the compiler will stop you. There is no plus operator that takes an option. You have to unwrap it first. To get the value out, you have to handle both cases, some and none. The compiler does not let you skip the missing case. It is not a warning, it is an error. Null pointer crashes do not survive that rule at all. The $1 billion mistake is kinda like opted out at the type level before any of the code runs. A struct can hold an enum. We gave player a status field, so Meow now has a status. Reading it back is the job of match. The first thing in the match line is the value you're inspecting. Below it are the arms, one arm per variant. The arrow points from the pattern on the left to what runs on the right. The match test top to bottom. The first arm that fits in the one that runs. The rest are skipped. The compiler still requires every variant to be covered, but only one of them executes. And here is the part people from older languages do not expect. Match is an expression. Every arm returns a value. The whole match returns a value. You can put it on the right side of a let, one line, one of the 4 answers, ready to assign. And when a variant carries a data, the pattern can pull it out. The next scene is just that. Match is branch plus value in one expression. Here is the move that ties it all together. A function plus 1, it takes an option of I32 and returns an option of I32 inside a match on X, 2 arms. None returns none. And the interesting one is sum. The I is the name and it binds to whatever number is inside sum. To call it with some 5, maybe we are sending the 5. The match looks at the first term, none, so does it fit? No. Second terms, some I, does it fit? Yes. And I is now 5. Right side runs and I plus 1 is 6. Returns some 6. Call it with none. First term, none, yes. It fits, right side runs, which is just none, returns none, and some I arm never even looked at. Match arms do not just branch, they pull data out into names you can use. Let's say you handle 3 statuses and forget. Game over. In a lot of languages, that compiles fine shapes and crashes the first time it happens. But Rust will not build it. The error reads non-exhaustive pattern. Game over, not covered. The compiler even names the variant you missed. Add a new variant to status later. Every match that touches the status breaks until you handle it. Sometimes you do not want to write every case, you want to handle a few, lump the rest together, the pattern, other. Just a lowercase name binds the rest. Whatever value did not match above, you can use it inside the arm. If you do not need the value, use underscore, same idea, but it tells Rust not to bind. The compiler will warn you about unused variables. Pure catch-all is just no name. Cover every case or use other to keep the rest or underscore to drop it. Sometimes you only care about one variant. A full match is just noisy for that. If let runs the block only when the pattern fits and binds the data inside. Think of it as match trimmed down into a single arm you actually cared about. And if you want a fallback when the pattern does not fit, you can chain an else. It is the same as match with two arms, your pattern, and an underscore catch-all. The else runs whenever the pattern misses. Either branch can return a value. It's like the same idea but for loops, while let keeps going as long as the pattern keeps fitting. Pop a player off the lobby, sit them, repeat. The moment pop returns none, the pattern misses and the loop ends. Decision: do you care about every case? Reach for match, just one case with optional fallback, if let, or if let else. Draining a stream while the pattern holds, while let. Match when it matters, if let when one case is just enough. There's one line above the struct that asks the compiler to write code for you. This is what derive does. Clone, copy, default, and partial equals. 4 pieces of behavior all generated. We covered debug in earlier scenes. Now let's go through the rest. Clone is the explicit deep copy called .clone, and you get an independent value you see call write in the code every time. Cloning is never silent in Rust. If the value was big or expensive, you would know because you typed that word. Copy is the surprise. If every field in your struct is itself copy, like numbers, boolean, the compiler can copy the whole value implicitly. Let b equals to a, makes a copy, and leaves a. Perfectly usable afterward. No move, no clone, just call. And just a bitwise duplicate behind your back. Partial equalizer is, or partial equal, gives you double equals. You can write a equals to b between two player states, and the compiler compare field by field. Default gives you player state : default, a fresh value with every field and its zero state. Useful for initial state, useful for testing. And it's more like you ask for what you need, nothing you do not. Every line of derive earns its place completely. Well, there are only 3 ideas that we just discussed over here. A struct, which is the shape, and enum is like the choices, and pattern matching is how you read them back. And that is all structs, enums, and pattern matching. Now you can probably model your own data in Rust, the shape, the choices, and the safe way to read them back. In the next video, we'll go over collections when one player is not enough. Maybe vector for many players, string for text, and hash map for lookups. So I'm super excited, so see you on the next one. Thank you so much for watching.